Hello everyone. We're going to be solving a problem on 2D rigid body equilibrium, okay? And this is an example of a cantilevered support or a cantilevered beam. Okay, so let me first draw the figure. Okay, so it's a problem. And here is the problem. So I have some kind of a box-like creature, okay? I guess I need to start off by making sure that it is indeed looking like a box, okay? So this box-like creature, it has one end of it fixed to the wall. Okay, so this is a fixed end here. Okay, so this end is fixed to the wall. Okay, and such a beam where the end is fixed to the wall is called as a cantilevered beam. And as I have specified in the past, right, so if you have a beam is any long body whose length is its largest dimension. Okay, so an airplane can be thought of as a beam if you think of it, or you can think of your pen that you're writing on as a beam, of some kind. Okay, cantilevered beam is an example, is what you're seeing here. So this is an example of a cantilevered beam. Okay, cantilevered meaning it is fixed to the wall. Okay, so I have a force acting on this body here. Okay, so let's say that there is a force whose magnitude is 100 newtons, and then I'm going to say that, okay, hey, there is a couple moment which is acting on this body. Okay, and this couple moment has a magnitude of 200 newton meters. Okay, and then we are told that the length from let's call this end as the end A. I guess let me go back to my regular color. So this is the end A. Okay, and then this is the end B, and the distance from A to B is given to me as 2 meters. Okay, so starting from here all the way down to where B is, I'm going to draw it in the form of a dotted line. As you know, dimensions, we typically draw it as dotted lines. Okay, and this is going to be a distance of 2 meters. All right, so what am I supposed to do in this problem? Okay, so find all support reactions at the fixed end of the beam. Okay, and a couple of assumptions that you are allowed to make here is that we can neglect the weight of the beam. Okay, so assume that the weight of the beam is negligible, which essentially means that the weight of the beam is probably smaller than the force that is acting on it, which is this 100 Newton force, and then we will also neglect the width of the beam. Okay, so neglect the width of the beam, which means that this is essentially a two-dimensional problem. Okay, so what is our basic procedure for all these problems? This is, as you will see, by the end of this problem, this is a fairly simple, straightforward problem. It is just to get ourselves started on this thing. Okay, we will go to more complicated problems as we solve more problems on 2D rigid body equilibrium, and you'll be seeing more of that happen. All right, so what am I going to do here? I'm going to first start off by setting up a coordinate frame. Okay, so my solution. Okay, set up a coordinate frame, and so this is something that I will draw here on the side of the page. Okay, so this is something that I will draw on each and every problem. Okay, so this is x-axis, y-axis, all counterclockwise rotations about the z direction is taken to be positive. Okay, so this is the coordinate frame. Then I draw the free body diagram. Here is how I draw the free body diagram. Look at this. I take this beam, and I wrench it away from everything that holds it in place, which means, you see, I'm just going to take this beam and just copy only that beam, and then I'm going to draw that person here. Okay, so you see, first of all, I have not marked the support. I don't see the fixed end here. Instead of drawing the fixed end, I will draw the support reactions on that fixed end. Okay, all right, what am I going to do now? And then I will see, okay, hey, what are the applied forces on the beam? There is a 100 Newton force, 200 Newton meter clockwise couple moment. I'm going to mark them next. Okay, so I'm going to have this 100 Newton force, which is acting vertically down here. Okay, and then I'm going to have this 200 Newton meter clockwise couple moment that is acting on this beam. Okay, then I come to the idea of a support reaction. Okay, so look at this. Let me go back to my regular color here. So support reaction. Okay, what are the things? The cantilevered end prevents translation horizontally. Okay, in both the horizontal and vertical directions. In horizontal and vertical directions. Okay, which implies that I'm going to have reaction forces in the x and the y direction. Okay, so this implies that we will have reaction forces in the x and y directions. Okay, that's one thing. The second thing is this. Look at this. Okay, so I hope this is obvious. You know, the cantilever, because it is fixed at one end of the wall, you're not going to be able to take this beam for a walk, right? You cannot move it horizontally, neither can you move it vertically, which means that you're going to have reactions in the x and the y direction. The other thing is this. I mean, if I'm looking at this cantilevered beam here, which is fixed to the wall, I will not be able to bend the beam or rotate the beam, because the wall is going to prevent me or resist me from rotating. Okay, so the fixed end also resists rotation, which means that we will have a reaction moment at the fixed end. Okay, so essentially here is how I think of it. Okay, so when I just draw a small piece of this cantilevered beam. Okay, so I just draw a small piece of this cantilevered beam. When I'm drawing the support reactions and when I'm thinking about the support reactions, I don't worry about anything else that is happening. I just focus only on this particular end of the beam here. Okay, so when I look at this end of the beam, right, I obviously see that, okay, hey, if I'm trying to travel horizontally this way or that way, all right, if I'm trying to travel horizontally, that is not allowed. If I'm trying to travel vertically, is that allowed for me? That is also not allowed. If I'm trying to bend this beam, if I'm trying to bend this beam this way or that way, the beam, because it is fixed to the wall, is going to resist me from bending. Okay, so which means this is also not allowed, which means I'm going to have two reaction forces in the horizontal direction, the x and the y directions, and I'm going to have a reaction moment at the fixed end. Okay, so let me mark that out here. All right, once again, the bane of my life is drawing these straight lines. All right, okay, so if this is the case, then you see I'm going to go back to my figure here and then mark the reaction forces. Now when I mark the reaction forces, I am not worried about what's happening due to the applied forces at all. I don't look at these applied forces, applied couple moments. I just choose arbitrary horizontal and vertical directions. Look at this. I can just say, okay, hey, I'm going to draw a reaction force here, and I'm going to call that as A suffix X. Okay, so these, and then I'm going to draw a reaction force which I'm going to point vertically down and say, okay, hey, this is going to be excuse me, A suffix Y. These are just drawn arbitrarily. Okay, so these are your reactions AX and AY. Okay, you can choose arbitrary directions up or down. It does not matter. Don't look at what's happening in terms of the applied forces. Do not look at them. Look at only what's happening on the fixed end. I'm just saying that, okay, hey, I'm just going to mark this force down and let the equations take care of it eventually. Okay? And then I'm going to have a reaction moment here as well. And I'm just going to assume that, okay, this reaction moment is pointing in the counterclockwise direction. And I'm going to call it as MA. And suffix R, or MR suffix A. Okay, so let's call it as R suffix A. Okay, and that's going to be the reaction moment here, which is MR suffix A. So I want to make a note. Okay, so, and I'll bring this one more, and one very last thing I got to draw is the dimension. Okay, so starting from point A to point B is a distance of 2 meters, as you can see. Okay, so this distance is 2 meters. Let me actually bring it down. Okay, so this is a distance of 2 meters. Let me mark it in the dotted lines, as you know by now. Okay, so this is 2 meters. And I want to copy this figure, all of these things, and I want to bring it onto the next page, and I want to make a small note. Okay, so note. So when you're marking the reaction forces and reaction moment at A, do not worry about the direction. Draw in any arbitrary horizontal and vertical direction, and in clockwise or CCW direction for the reaction moment, and let the equilibrium equations take care of the actual direction, or let the equilibrium equations tell us the actual direction. Okay, this is very important to understand. Okay, so this is the situation here. So then I'm done with the free body diagram. What are the ingredients of a free body diagram? 3 things. First is, do I have all the applied forces acting? Yes, I do. 100 newtons and then 200 newton meters. Do I have all the reaction forces? Yes, I do. AX, AY, and M R suffix A. Okay. And then do I have the dimension? Yes, 2 meters. Okay, so the AX and AY, these are the support reaction forces. And then MR, A is the reaction moment at A. Okay, then I start making use of the equilibrium equations. So let me start using that. I say, okay, sum of all the forces in the x direction, all the forces pointing to the right are equal to 0. Very important, set them equal to 0. Do not forget that. Okay, what are the forces acting? The only force acting I see is this force AX, and it is pointing to the left, which means that I'm going to write it as minus AX. Okay, so this implies that minus AX is equal to 0, or obviously AX is equal to 0 newtons. Then I say, okay, sum of all the forces in the y direction is equal to 0, and then all the forces that are pointing vertically up have to be set to 0. What are the forces that are pointing vertically up? I go to my figure here. AY is pointing down, 100 newtons is also pointing down, which means both of them have to be written with a negative sign. So this is going to be minus AY minus 100 is equal to 0. which implies that AY is actually equal to minus 100 newtons. Okay, so what does this tell me? So this tells us that we chose the direction of AY wrongly to begin with. But wrongly is a bad word to use here, because when I have a problem with many forces, how on earth am I going to know what the right direction is for AY? I mean, since I have only one force here, I can find out by just looking at the figure and saying, okay, hey, AY has to be pointing up. But if I have like 7 or 8 forces, without summing all the forces up, I cannot do that, right? So which means to start off, I just choose an arbitrary direction and then I let the equilibrium equations shake it off. Okay, so this tells us that we chose the direction of AY without looking at the equilibrium equation. So I don't want to say wrongly here, because that gives the wrong sense. Okay, so we chose the direction of AY to be opposite to what it was supposed to be. Okay, and this can be only found out only upon solving the equations of equilibrium. And AX is equal to 0 Newton implies that there is no force in the x direction that is applied, so which means the reaction force is 0. Okay, and then lastly I come to an important point in this problem. I need to find the reaction moment. The reaction moment is an unknown quantity, right? So I have 3 unknowns in this problem. There are 3 unknowns. So how do I find the third unknown? Is by doing the following. I can sum moments about any point on the body. Okay, so let me take this figure here. Okay, and then let me come and then bring it here. Okay, so to find, let's say, so to find MRA, I need to get that comma right. We can sum moments about any chosen point. Okay, so let me bring my figure down here. So, and what is a good choice here? You see, a good choice is the point A itself. Okay, so let me choose. I guess that's not what I wanted here. So let me sum moments about point A. Watch this very carefully. I'm saying the net moment about A, all the moments that are counterclockwise are taken to be positive. I'm going to set them equal to 0. Now watch this. MRA is a moment that is acting at the point A, so that is going to be in the counterclockwise direction, so I'm going to have to put it into the mix here. Look at the forces AX and AY. They are sitting at the point A, which means that they are not going to contribute to any moments about the point A. Okay, then look at the 200 Newton meters. It is clockwise. I say counterclockwise is positive, so this is going to be minus 200. Then I'm going to have the 100 Newton force. If I look at the 100 Newton force, line of action of that force is right here. I see that the perpendicular distance to the line of action from the point A is going to be a distance of 2 meters. Sense of the moment, right hand rule, fingers aligned with the force, my palm faces the point A, curl my fingers clockwise. So this is going to be minus 100 times 2. All of them set equal to 0. Okay, which tells me that MR comma A is equal to 400 Newton meters. Okay, positive sign says we chose the correct direction to begin with. Okay, if we got a negative sign, it is not a problem. Okay, so if we did get a negative sign for the reaction force or moment, it is not an issue, because we do not know the signs of these things to begin with. Okay, we do not know the signs of all these to begin with. And we let the equations of equilibrium tell us what the signs are. So we solve and let the equations of equilibrium tell us the proper directions. Signs or directions. Okay, so that's about the end of this problem. I'm going to go back and very briefly look at it again. Okay, so I have a cantilevered beam to begin with. What's a cantilevered beam? It's fixed at one end. I have some force acting on it. I have a couple moment acting on it. I need to find the reactions at the fixed support. How do I do this? I first draw a coordinate frame. Then I draw the free body diagram. What do I have on the free body diagram? I have the applied force. I have the applied couple moment. Then I have the dimensions. What else do I have? The support reactions. This is a cantilevered support, which means that it prevents translation in all the directions, x direction, y direction. So I'm going to have two support reactions in the x direction and y direction that represents the fact that I cannot translate in those directions. Then the cantilevered beam also prevents me from rotating or resists rotation, which means that I have a reaction moment here, which tells me that, hey, this represents the fact that the cantilevered beam will prevent you from rotating. I have three unknown quantities. I have three equations of equilibrium. When I draw the support reactions, I don't know what the actual directions of AX and AY are. Is it to the right or is it to the left? Is it up or is it down? In this problem, it's simple. I can directly see that AY has to be pointing up. But if it's a complicated problem, I don't know what the directions of AX and AY are to begin with, which means I don't want to take a risk. I'm just going to assume some direction for AX and AY, and then I will let the equations of equilibrium tell me the actual direction. Okay? So I just assume some directions. Okay? So that's a statement that I want to make. So assume directions for the support reactions. Okay, and then I say, okay, after I sum forces up, I get AX is equal to 0. After I sum forces up in the y direction, I get AY is equal to minus 100, which tells me, hey, dummy, AY is actually not pointing down, it's going to be pointing up. But that's okay, because I did not know this to begin with, and I'm just telling, okay, let the equations tell me the truth. The equations cannot lie. I can lie to myself, but the equations never lie. Okay, and that's what the equations are telling me here. And then lastly, I have summation of the moments. Be very careful. When I'm summing moments up, do not forget this M or suffix A for a fellow is or she's sitting or they're sitting right there. The forces don't contribute to any moments at the point A because there are no perpendicular distances for those forces. But this is a couple moment. A couple moment, no matter what it is, no matter whether you are taking the moment at the point where it is acting, it is still going to contribute to the rotation. Okay, that is a fact of life. Okay, you got to accept that. And then I have another couple moment that is acting here, and then I have a force times a perpendicular distance, which is 100 times 2, and then eventually I get a positive sign, which tells me that, okay, I knew or I chose the proper sign to begin with. But this is just pure coincidence. I did not know. I did not look at the problem. When I drew the support reactions, I never even looked at the applied forces. Okay, and so if you did get a negative sign for the support reactions or force moments, it is okay. It is not an issue. Okay, this is because we don't know what the signs are to begin with. So we solve the problem and we let the equations of equilibrium tell us the sign. I hope this has been a useful exercise for all of you. Take care of yourselves. I'll see you in another problem. Bye-bye.